Hello, good afternoon. I'd like to thank Yui, first of all, and all his team for asking me along and the other speakers today to have got together such an interesting panel of people. Before I begin my presentation, if I'd like to, I suppose dialogue is what these events are about. If I could just reply to a little bit of what Lisette was talking about. We in France at the moment have brought in a law where I think we're the first in the world, where with our planning application we have to put the kilogram equivalent CO2 of the building we are proposing to build. And that's having huge implications in everything we do. What I'm doing now, I did not do 2 years ago, or it was unimaginable 5 years ago. So if I could just give a little feedback on that sustainable aspect to you in China. I remember telling facade contractors in France about 5 years ago, you have to build your facade units out of wood. And they said, but we do aluminium. I said, well, you can do what you like, you know, okay. They are now all testing facade units in wood. Every big contractor in France, that's where they see the future for, not for high rise, but for low rise. So between you as here today, the whole aluminium industry, my advice from the cold face of France in designing facades is the majority, if you go the same way, the majority of French contractors, more than half the work is retrofitting. That was unimaginable a few years ago. Now they are retrofitting for more than half their turnover. And timber is starting. They don't know where it's going to go, but they're starting the testing and getting the ADV technique and the official approvals to build in wood. So it's a very challenging moment. The other thing, I just gave in a competition for a hospital using these new targets. All the aluminium cladding systems were impossible to get through the new targets because of the aluminium supports behind. So behind the aluminium, the Aluca bonds and so on, in the French way of testing the carbon footprint, aluminium is very handicapped because it's not sufficiently recycled yet. And in that context, I ended up for the metal cladding putting zinc fixed in a traditional way onto timber studding panels, because all our infill panels are now timber studding. So, and the concrete panels had to become fibrous cement panels to get so little material into the panel that they could get through this carbon footprint loophole. So it's very, very interesting times ahead of us. Now I'll start the real presentation. So Tess, we're a company, there's three of us. We previously worked in a company called RF4, which may sound familiar to you from RF4 China, who you will know, RF4 Shanghai. We worked together with three partners in 2007, left RF4. I had as an intern who was doing his studies, Yui, was working with me 25 years ago. And we came together and started working in Shanghai. And so I've been working in China for the last 20 years, but I'm not going to show you much of that today. So I just want to show you, Yui said I wasn't to talk about building in timber and building low rise, I would show fun projects. So that's what I'm going to do. I'm just going to share with you some nice projects. He said, can they be international? Okay, this is as international as you can get, the Olympic Games. So we were responsible for, whoops, I'm trying to see if I've got a light. We were responsible for these Olympic rings. The key element is that it was originally the 5 continents, and the black continent is very hard to light up, which was a technical problem in designing how to hang these rings off a structure which is 139 years old, the Eiffel Tower. So as you can see, when a person is sitting next to the installation, they're quite big. They're 30 by 10 meters, they weigh 30 tons. And the idea was we'd hold them proud. We were the only designer involved with the project. And so we decided to hold them out from the facade so they'd float. So that's done by a little isostatic structure of struts and cables which prop them out, which pick up these 4 intersection points. So the problem was how to hold them onto these old structures, this old steel structure made out of plates. This is what the Eiffel Tower is basically made of. The legs, the main element on the legs are just these little plates riveted together. So what we didn't want to pier to, it's only a temporary installation, so we clamped onto, there's a little pads which distribute the load behind these clamps, which were pre-stressed, and they would transfer the loads downwards. The actual rings themselves, how to light them up. Again, the problem was you can't light black. It doesn't show up. So if we just lit them, we could have maintained the colors at night, but we would have lost the black planet, the black ring in the middle. So what we came up with, this was a test we did in the workshop, in the office, where during the day we perforated metal which you can see the color of, and then you light it and you no longer see the color. The eye will pick up the brightest source of light. So we have lighting in the inside of the hollow, and they got hung up by 2 cranes. There was a little jig was put into place to hold the struts and the cables in the final position. So when the rings came in, all the support structure was in the right place. The complexity turned out to lift out this jig after the installation of the rings. And there they are. And that's the image went around the world. So this is the work we were involved with. It's been seen by the most people in the world. So the thing we're best known for in France is having been involved with this rather complicated structure by Frank Gehry, who died recently. So Frank Gehry, his team worked on the model on the bottom. And then this model was scanned, and then using CATIA, those who were watching the presentations this morning about the importance of BIM and 3D modeling, this project could only have been done with all the 3D modeling. So we were involved with the glass sails, the sail structure, the meringue-like iceberg structures, and the glass infill. I won't talk about the glass infill, I'll just talk about the others. So here we have the sails. So we knew the surfaces were developable surfaces because they'd made a physical model. Gehry didn't make a computer image, they made a paper model. So we knew if you can make a paper model, it's a developable surface. So the scan from the model was the reference surface, which automatically you can find easily in Rhino your curves, where the curvature is. What was complicated was finding the appropriate mapping surface. In the end, we used geodesic lines, which is the shortest line connecting 2 points across a curve. But after many variations of what was X, Y, Z parameter, we ended up with this glazing pattern. The trouble is, within each glass panel, it will not have the exact same geometry as its neighbor, so the line won't be perfectly flush. So that was the parameter, which was an architectural judgment as to what degree of non-alignment we could put up with. The glasses, having looked around here, this is pretty old stuff now, I realize, because our oven could only make curves, not double curves. So we'll do it again with double curve geometry the next time. But we had the single curve geometry with an oven with a movable bottom, and each glass panel had a radius and also had an axis along which the cylindrical geometry was defined. And we fed it through this oven. That gave the almost perfect glass, which had silicon jointed elements down either side, which you can see here, onto little rotool fixings onto the support structure. The main structure, I haven't much time, so I'll just, relative to what was said this morning about redundancy and sequential collapse, one of the complexities was we undertook all these sales structures to do sequential collapse analysis, where we basically knock an element out, see what would happen. We discovered, having been around all the sales, there were about 4 or 5 elements did need to be redesigned, reinforced, replaced, or whatever, due to this analysis. The other thing was a little complicated, was the timber is actually frequently double curvature. So the banana-like elements with a double curve. So the glue lamination was first made like a conventional glue laminated element on a single curve. Then it was sliced up like sliced bread to be re-glued with a curve in the other direction. So if you look at the end grain of these timber elements, it's actually like a chessboard. And all of that. On the glass sails, the skin, what was interesting, there's a reflective coating on the outside, but there's also, which reflects what's happening around and gives a materiality. But there's also a slight screen printed dot pattern, which when you're inside gives it like, you feel like you're under a tent with a sense of enclosure. So there's a lot of work done on the actual quality of the glass. If you haven't been to this building, I'd really advise go into it the next time you're in Paris. But the gallery spaces are they're gallery spaces, they're white boxes. Go upstairs, out onto the roof, into this most amazing space I think you'll ever visit. One of the qualities given to that space is the surfaces of what Gary called the icebergs. So how do you manufacture those forms? Well, they're basically made up of shells which provide the weathering element to the building. These are the shells which were actually fabricated in India. They're totally monolithic. You can see the isostatic performance given by the struts which prop it out. So these monolithic shells are assembled on site and weathered. These dots which you see here actually take plates. Now the role of those plates are to receive the almost ceramic-like tiles. These are ductile, which is a high-strength fibrous fibrous cement panel. So these plates, these give the geometrical reference for all the cladding. So the only tolerances are taken at the edges of these plates, and the cladding goes straight onto the plates. So the fabrication of those plates, you can draw everything in 3D, but it's very hard to make it in 3D. In the end of it, we came out of it saying, it's not in God we trust, it's in 2D laser cutting we trust. You can cut so accurately in 2D, and then as long as you generate your 3D from those accurate 2D elements, we felt we were safe and sound. There was one element we had to actually ground, we couldn't just cut it, which was the panels. So these panels, the geometry was given by grouting out form on these polystyrene blocks. These polystyrene blocks, each ceramic tile has a polystyrene block onto which is placed a mold. The mold, there were very few molds. It's the same mold used again and again and again. And that's placed on top of the form giving. And the fibrous cement is poured in, it's sealed up, and so on. Here you can, there's a site project photo, so there's some of them missing. But you can see if you place one panel on the surface, that generates all the rest, because each surface in its projected shape is the exact same each tile. I think that speaks for itself. I don't need to say anything. It looks wonderful. They came back, the team, and said, we have another project for you. And this time we want stainless steel blocks. And each block is to be wrinkled. So it looks like a cliff face. It's based on a local cliff face. So this was done in the same way we made the shell structures, which were prefabricated. In this case, in the previous project, the insulation was outside the shell structure and then the membrane. In this case, we installed it without the water insulation. Insulation was projected, and we were able to do this because we could justify not having, despite saying here we have a vapor barrier, we had no vapor barrier on the inside, and we're able to justify that due to the local balmy climate in the south of France. So onto those forms were craned in, and on the outside of those forms were shelves, and onto these shelves were brackets which held the blocks. The blocks, it was a bit of an industrial secret how the blocks were made. Several Gary likes asking contractors to come up with ideas. So we asked different contractors, there was a bit of a beauty competition, who could produce the kind of a wrinkly surface that Gary would like. And the people who won it won the contract, and they had a procedure of heating and contracting the block, which would give it the buckling effect. Totally random, so each block has a different buckled effect. The blocks can be replaced, which was the key for those brackets. This is a third art foundation. This one has just opened in just before Christmas. It's a few weeks open, so it's by Jean Nouvel, who's still alive. And that ceiling there is actually a floor which comes up and down on these mechanisms which are here. So with inside the building, which is next to the Louvre on the Rue de Rivoli, there's a city block on the whole ground floor, and the basement is an art foundation for Cartier. So the buildings actually was renovated. A large part of it is concrete, although the original colonnade is the original built at the time of Napoleon. So because it was concrete, we were able to do a lot of things. One of the things Jean Nouvel wanted was that the glass frame would be totally invisible and you would not see the glass frame, which is incredibly efficient with the 6 by 3 meter sheets and the frames concealed. So as you are walking through Paris, you can look in to this art gallery. I had a glass of champagne at the opening and was looking out, and there were tramps going to the toilet outside the window, and life going on as it does in the street. So it's a wonderful giving art to the town. The secret to the building, what's amazing, is the ground floor has been taken out and the floor level of the parking below, so that there's a huge space opened up inside the building, which is the length of 2 football pitches. It's about 150 meters long, this space. And inside in that space, the floors can move up and down. These are the columns which were left in place, which hold the building above, which stayed in use during the whole building site. We were very involved with these roof lights in courtyards. There's several courtyards in the building, and when you're in the building you can look up and you'll actually see trees, and the trees are planted in these big planters, between which are the glass, and these grey elements move over and can seal off the space if the curator wants to black out the space. So every 6 months there'll be a new art show which will be created by a different person, and he can move the whole building around. All the floor plates move up and down, and he can make whatever kind of space he would like. What I personally enjoyed doing most was this 150 meter long canopy on the outside, which is quite simply it takes 30 years of experience to do almost nothing at the end. This took about 3 minutes to conceive of this. It's just, there's a tube and you hang a sheet of glass and it's propped back off the building by these tubes. There's a little gutter which takes the lateral thrust out of the props, and the water from the gutter goes through the water pipes back in. It's so simple and minimalist. Another minimalist little glass engineering project, not as funky as Agnes's this morning, I'll admit. It's very modest, only 8 meters long, but we like it. There's this little glass extension on the side of Dior's headquarters with 10-meter high sheets of glass and an 8-meter span. So we went through, I was going to talk about this, but you go through what Agnes said this morning about this, sequential testing of rupture and so on. We on the 5-layer laminate, we just silicon jointed a little stainless steel profile, which takes a conventional Ryco system. A lot of the complexity, like anything, it's like designing a bridge. You spend more time designing where the bridge lands on land than you do sometimes designing the whole bridge. So a lot of the energy went into where we come in and meet the existing building and hide the blinds and so on. This is just to show I do really work in China. This is a project in Shanghai with glass blocks. The basis was we took a glass blocks, mitered 2 blocks together and glued them, sandblasted them, and it made Gartner were involved with building this. That's for Michael if he's present. And the glass blocks, when they cantilever in this geometry, they're held by a little plate, which itself is supported by lateral plates, which have this form so that light can come in and they can be backlit at night. So all those little plates make this honeycomb structure, which are held on a steel structure and support the glass blocks. In Hong Kong, closer to here, if anyone has seen this lately, I'd like to know how it's weathering, by the way. I haven't seen it in quite a while. Their glass Murano lights are hung behind a sheet of glass and in front of a sheet of mirror. So you get twice as many expensive Murano chandeliers as you think you are getting because of the mirror. The issues involved, which were complex, I was worried about dirt and cleaning in here was impossible and condensation occurring on the glass. So we plugged the facade into the air conditioning system. I know it's not very responsible, but it did keep the facade clean and dry. And for maintenance, you remove the top and you can pull up the strings of lights. And this is the little mirror glass, discrete little fixing that holds the glass in occasionally at the intersection points. So to come back to Paris, there is one tower in the middle of Paris, which is much hated, which is this little black 150-meter tall tower in the middle of Paris. So I was involved in the competition, which won the competition to redesign it. So the team, we kept the basic form of the shaft, but what was interesting is building in an existing city, which is not the kind of problem you have a lot in China, but in Europe we do. So what we did was we cut out the bottom third was to be the scale of the surrounding buildings. Then there's the shaft, and then there's a public space which is open to everybody at the top. So we divided it into 3 parts with winter gardens accessible at mid-level and up at this level, and then the glass house itself at the top. The facade, the main bulk of the facade had 3 ideas behind it. One was to have a big sheet of glass which was 5 meters by 3 meters, which would break the scale of your normal 1.35, whoops, I better go quicker, 1.35 module. We also put a shiny coat. We also had very little solar coating, just low E coating on the inner glass, because we got blinds. The blinds are protected by an outer sheet, classic double skin, but we made it into a damier pattern, these big panels. These big panels the reason behind the big panel is because we're involved in Paris. You cannot demolish buildings. You have to keep the concrete frame. So everything we're doing in Paris is retrofit, is reskinning 1980s, 1990s buildings, going back to after the war as well. So here, because we could not reinforce the edge of the facade to support our double skin facade, we're increasing the weight. So what we did, so the facade itself spans the 5 meters. This was the origin of the 5 meter block and the 5 meter sheet of glass. So the block spans, so we did not have to reinforce the edge of the beam. So this is the steel part of the facade. That's all wrapped up in aluminium and insulated. And then you come with your outer skin facade. There's also a whole idea about natural ventilation. Because the damier, we got high pressure points and low pressure points happening because when the wind, which dominantly came longitudinally along the facade, the prototype being installed here, which is not at all black. This was interesting. It's a software called Ocean, which has the characteristics, the physical characteristics of the glass reflecting, absorbing light qualities and the color reflection. So you can actually use it to tell at different times of day, different times of year, different locations in the town what your building will look like. Another tower I'll quickly go through, again a rehab of an existing tower. This was a concrete tower with a concrete wall with these punched holes, which we as a team really liked. For information, we always do our conception by hand because there's a real idea of from the hand to the brain, things go very quickly when you're drawing by hand, you get ideas. We proposed just recladding, insulating it and re-putting the aluminium shields that we liked. The client thought that was a terrible idea. He said, I want a modern building. So we covered it, the whole tower. We took the windows out and we put a new glass skin on the outside, which you could look through from the inside. I said, this is going to overheat, it'll never work. We'll get so much heat building up in behind that sheet of glass. Luckily, we had a tower to the south. This is the energy gain without that tower. Thanks to the tower, we had much less. We had some problems here. We calculated it to see what the heat building was. We discovered because of the absorption of the concrete, the thermal inertia of the concrete, it didn't get that hot. So we're okay, so we built it. Here it is being cladded up. There was a little band of insulation which is very pronounced in this drawing. Other directions you can hardly see it. And there it is today as it's built and at night. A last project very quickly. We've started working in Africa, which is fun. So this is in the Ivory Coast. They have money in the Ivory Coast because they export a lot of the cacao nuts which make chocolate come from the Ivory Coast, so they have a bit of money. And they wanted an iconic tower, so they have this very tall 400-meter high tower. We said we'd do it much simply. The architect gave us a little model. It was like winning the Oscars. You had the little trophy. And we photographed it, and based on the photographs of the little model, we just gave the XYZ coordinates. So it's a very simple descriptive geometry approach of how you create the geometry, which we then gave to the engineers who did the structure following our geometry. The facade, because of the very high sun in the Ivory Coast, it's this little bit here that does all the protection for the facade. There's no solar shading. We use additional protection from this outer skin. The outer skin is really there to give this play of depth. We didn't want it to look massive. We wanted the tour to look like it had a depth and a richness to it. So there's an over facade which has gaps, so you can actually clean the glass. There's no cleaning cradle from the top, which would have been complicated because of the geometry of the negative slopes. So you actually clean the glass through the gap. And we slipped this the horizontal projection is not aligned with the floor, but is lower down, which means you can see the town, and it also gives better protection to the floor below. There's a little prototype, there's a little drawing showing the two. The inner facade, very simple. The outer facade, it's been installed, it's nearly finished at the moment. You begin to get a feeling of the depth of the difference between what it would have been like if it was a single skin facade or a double facade. Well, as a double facade, it's really when you move around that you see the movement of the facade. And there on the top, we've got a big space on the top. It's okay, so that's a tour of some of the projects that we're doing. Thank you.